Okay, the quantity 556.2 times 10 to the minus 12 seconds in nanoseconds. So to do that, we need to do a conversion here. How many nanoseconds are in a second? Well, what if we don't know that? How can we figure it out? If you don't just know the number, what's a good way to figure it out? What? Yeah, the way that I think about it, rather than remembering the individual numbers, I think about the order that they are in. So you've got like second, and then going smaller from second, we've got millisecond, microsecond, and nanosecond. So you kind of keep that order in mind. Second, so it goes whatever the unit is, then you've got milli, micro, and nano. What do you have the other way? What's bigger than second? What's the next prefix from just the normal unit? Anybody knows? All right, you should know these. Kilo, and then mega, and then giga. So know at least three prefixes in either direction. You should be okay. So going the other direction would be kilo. Whoops. Then it's a big M, mega, and a big G, giga. Okay. So then you can count 10 to the third. So each of these are 1,000 times different. So if this is 1, then this is 10 to the third smaller. Whoops. So if that's 1 second, that's 10 to the minus 3 seconds. That's 10 to the minus 6 seconds. That's 10 to the minus 9th seconds. So then a kilosecond is a 10 to the third. Mega is 10 to the 6th, or a million. Giga is 10 to the 9th, or a billion. So it goes by thousands. Okay. You don't know that already. So that way, as long as you keep the order of information prefixes in mind, you can always figure out what that number is. So a nanosecond is a billion times smaller than a second. So there's a billion nanoseconds in a second. Now we can do the conversion. 556.2 times 10 to the minus 12 seconds times, we want to get rid of seconds and end up with nanoseconds. And you can do this conversion however you want. You can say that there are 10 to the 9th nanoseconds in a second, because a nanosecond is smaller. Or you can say there's 10 to the minus 9 seconds in a nanosecond. Right, just flip it over. Either way is right, but you got to keep in mind in your head, a nanosecond is smaller than a second. So therefore, our number should be much, much bigger in nanoseconds than it was in seconds. All right, so 10 to the minus 12 times 10 to the 9th is 10 to the minus 3. So that means we have 556.2 times 10 to the minus 3 nanoseconds. Okay. And really, once you get used to this, you probably don't even need to set up the conversion. You can just move the exponent down by however many or up by however many you need to do that unit conversion. That's what makes the metric system so convenient. All right, any questions on that conversion? Okay. This one look familiar? We did that in class, right? It's also in the homework. So I won't go through it again here, but it comes out to something like 4 cubic centimeters, or 4,000 cubic centimeters, right? That's right, 4,000 cubic centimeters, something like that. You can go back to the notes and get that number if you are curious. Okay, now this one we need to read a temperature properly and then convert it to Fahrenheit. So this is a thermometer in degrees C. Let's zoom in a little bit. So that line looks to me, and since you're looking at this printout and who knows how the resolution was in the printout, you know, that's why we estimate that final digit. We could have a little bit of a range here of correct results. But when we're zoomed way in, looks to me like that line is exactly on this tick right there. like exactly to that tick. If you saw it a little bit one way or the other, that's fine. That's how measurements work. But I'm going to go with that for now. So that means that it is definitely between 36 and 37. So it is for sure 36 point something. And then that is the 1, 2, 3, 4, 5, 6th tick. And then I'm going to estimate that that's at 0 because I'm going to estimate that it's right on that line. Right? So that means that you should be able to get 4 significant figures from that particular thermometer. Because you can get the 36 from the big numbers, then the 6 from the tick, and then the final digit will be your estimate, depending on where you saw it. So plus or minus 0.01 or 0.02 or something like that. But if you just put 36.6, that is not correct, because there is a higher level of precision on this instrument. Okay, so then we convert it to Fahrenheit. How do you convert from Celsius to Fahrenheit? Yeah, we're going to multiply by 9/5 or 1.8. And then we're going to add 32. And that comes out to about 98, but might as well do it properly here. I have a calculator in my telephone. So it comes out to 97.88 degrees Fahrenheit. Okay, and keep those 4 significant figures. Sound good? All right, let's move on. Back page. How many moles are in 11.0 grams of manganese 2 nitrate? So after today, I should note, after we do this naming stuff in this chapter, you'll need to be able to find that formula from a name. So rather than saying MnNO32, I might just say manganese 2 nitrate, and you should be able to write down that formula. And in fact, you'll have to get it right to be able to get the mass right. So we'll work on that today. But for now, we've got this. So we need to find the molar mass and then do that as a sort of a conversion. So to find the molar mass, we're going to look up manganese. And the mass is 54.9. And then we've got 2 nitrogens, and those are each 14. And then 6 oxygens, and those are each 16. And so that mass comes out to, assuming somebody did it right, is it about 120? Not everybody's showing their work here. So all right, we'll just calculate it out. That's fine. So I've got 54.9. $178.9. So we'll say 179. That sound right? And that's grams per 1 mole. So grams per mole. All right. So then we can put that in to solve for moles. So we've got 11.0 grams, and we want to go from grams to moles. So we're going to use that number, 179 grams per 1 mole. And that gives us 0.0615 moles, or 6.15 times 10 to the minus 2 moles. All good? All right, great. And this one has a couple extra steps on it, but if you set it up as a conversion, it still works just as well. So we've got to figure out, since we're looking for molecules in a volume. So we're going to need to go, let's kind of set up a plan here. If we ultimately want to know molecules, what do we need to know before we get to molecules? What are we going to get molecules from? From moles, right? Because it's a count. So we have to have moles to be able to get molecules. And then moles we can get from mass. So that's going to be, in this case, grams. And then we can get grams from the volume using the density. So our conversion is going to be going from volume to mass, and then to moles, and then to molecules. All right, so let's set that up. We need to know the molecular weight, or the molar mass, of antimony pentafluoride. So that's going to be 121.8 plus 5 times 19.0. It's going to be 217 for antimony pentafluoride. So that means that our whole plan here is going to look like this. 2.50 ml times, our density is given in grams per cubic centimeter. We know cubic centimeter is the same as a milliliter, so we don't need to put in an extra factor there. We can just say that we know that the density is 2.99 grams per milliliter. That gets us grams. Then we can go grams to moles using our molar mass. And then moles to molecules using Avogadro's number. Okay, we put all that together. And get something like 2. Something like 2.07 times 10 to the 22. That sound right? Okay. All right, and so that's a quiz. All right, so those are indicative of types of problems you'll see from chapter 1 and 2. We've got measurement, we've got unit conversions, and then some molar mass type conversions that we'll use more in the next chapter when we get into chemical equations. Please keep up with that. I think the chapter 2 homework is due on Thursday, and then chapter 3 homework will be due at the end of the weekend. That should go up today. Where's my other notes? There we go. All right, let's talk a little bit about the periodic table, and then we'll get into, actually, then we'll probably take a break and get into some naming and then do some practice like we did yesterday in lab. Okay, so you know a little bit about the periodic table. If anybody can't see that well, you might want to come back up and grab the one that you left, or if you've got a book or your lab notebook, those probably have periodic table in there. Also, we'll be referring to that a lot today, so you'll probably want that handy. Yes. All right. So we got our periodic table up there. We know a little bit about how to use it from our mass calculations, right? Let's talk a little bit about this particular separation, metals versus non-metals. So have you heard of this before? You know, something about the difference between non-metals and metals? How do we separate metals from non-metals in the periodic table? How do we know whether something's going to be a metal or a non-metal if we can't actually see it and test it out? Yeah.
The line.
Yeah, the line, which has been emphasized on this one and looks like blue marker. You see, everybody see that going up on kind of the right side there, zigzagging downward? Roughly, everything to the left of that is a metal, and everything to the right of that is called a non-metal. And these groupings are based on their properties. So metals are shiny, they tend to conduct electricity, they're malleable and ductile. What does that mean? Heard those words before? Yeah, it's kind of like how it squishes. Malleable means it can be hammered into a sheet. So you take a metal and you hammer it, and it kind of bends or dents. Right? Have you ever taken a hammer to the side of your car, it kind of bends, or maybe someone else's car. Actually, probably don't do that at all. But it bends, as opposed to a non-metal, where what would happen to a non-metal if you hit it with a hammer generally? It breaks, it shatters. So it's not able to be kind of spread out in that way. Ductile is similar, but it has to do with wires. Ductile means, or ductile means that it can be pulled into thin wires. So you can make wires out of metals in ways that you can't with non-metals. Now these are, of course, generalizations, and there are always exceptions to these things and various special formulations, but in general, these things seem to apply and seem to be true. Another nice thing that you can think about is how they what they do with their electrons. Metals tend to lose their electrons. They tend to form positive ions. It's unusual to find negative ions of metals, although they're known, they've been made. But generally, metals make positive ions. Non-metals can make negative or positive ions, generally negative. They tend to gain electrons, and beyond that, they tend to form covalent bonds. They tend to share electrons with other non-metals rather than forming ions. When they're in compounds with metals, that's when they usually form ions. And so the metals usually give up the electrons, and then the non-metals usually take them. The elements right along that line, so boron, silicon, germanium, arsenic, antimony, tellurium, those are called the metalloids, or semi-metals, because as you might expect, being right in the middle, they kind of have properties of both. So some of them can be more metal-like, some of them can be more non-metal-like, depending on their compounds. They're often, like silicon and germanium, are semiconductors, which means they don't conduct electricity as well as a metal, but they're not as insulating as a non-metal, so they're kind of in the middle. So there's a lot of sort of weirdness that happens right along that line. But in general, the ones on the left are the metals, the ones on the right are the non-metals. Okay. And then we have a few names that you should know from some of these, for some of these groups because of their very similar properties. You've got the alkali metals on the left, column 1, alkaline earth metals on the second one in. We already talked about those in terms of how they form ions. Then you have the halogens, which are group 17 or 7A. That's fluorine, chlorine, bromine, and iodine. They form 1- anions, right, gain electrons. And then the noble gases, which are the final column over on the right, tend to not react much at all, except in special circumstances. They tend to be really fairly unreactive for reasons that we'll talk about later. And then there are some other names. There's pnictides and chalcogens, which are the kind of some of the lower ones and some of the other columns. You don't need to know those names. Oops. So let's go on and talk a little bit about naming, because this is going to be something that hopefully you don't have too much of a problem with, but it's something that a lot of people always struggle with, because it's really one of the only parts of this course where it's just straight up lots of memorization. You just have to remember a lot of stuff. Most of this course is working out problems, is figuring stuff out, but this part is really just remembering some rules and then remembering a bunch of names. So we got to get started on that now, because it's something that we're going to use for the entire semester. We're always going to be naming things. We're always going to be talking about it. We we can't talk about the rest of chemistry without knowing names, because we won't know what each other is talking about. If I say to you manganese 2 nitrate, I need you to know what I'm talking about in terms of what that compound is going to look like. And that's true across all kinds of chemistry. So when you take organic chemistry, you'll learn some organic nomenclature. And any kind of career that you go into that is even slightly related to chemistry, whether it's medicine or environmental stuff, you have to be able to know what each other is talking about. So having a certain facility with chemical names is always really important. Even though it seems tedious, it's going to become really, really important no matter what you do, unless you are completely removed from all chemistry completely, which won't be the case because you love it and it's so much fun, right? Obviously. Anyway, so a lot of chemicals have these kind of common names. They were discovered in some way and somebody gave them a name because of what they were calling them. So you might have heard some of these names before. Some maybe not. Laughing gas. What's laughing gas? You know, the other name for that? The chemical name for that? It's called nitrous oxide, which is actually also another type of a common name. We'll get into that later. So there's all these different names for things. Sometimes scientists in one part of the world called it one thing, and scientists in another part of the world called it another thing, even in the same language. So there was this need for some kind of standardization, because otherwise there's a bunch of names for stuff and we don't even know what each other is talking about. So we come up with these naming conventions, which are just arbitrary rules that somebody came up with. They're not magic, they're not perfect, but a group of people came up with these rules and said, look, let's use these specific rules and then we'll always know what we're talking about. We'll always name these things the right way, and as long as somebody knows the rules, like you all, there won't be any confusion as to what this thing is called. We'll all know what it's called. So to do that, we have to group our compounds into different categories, because different categories of compounds are named a little bit differently. And we're going to go through some of these different categories and talk about what those names are and how they're constructed. So what do you think a binary compound is? A compound composed of how many elements? 2, right? Binary means 2. So our first type, our type 1 compounds, are going to be binary ionic compounds. So that is compounds made of ions that just have 2 different things, a cation, the positive ion, and an anion. The cation's written first and the negative anion is written second. And that's kind of the convention for writing these things. So let's look at some. Here are some examples. We've got NaCl. You probably know that one. What's the name of that compound? Sodium chloride, right. I'm going to list a couple more. Potassium sulfide, calcium oxide, aluminum oxide, let's look at specifically what the different ions are called in this type of situation. This is probably the easiest. These are going to be the easiest names once we have things in the category. What do we say for Na+, that ion that's right here? How do we name that in a compound like that, like this? It's not a trick question. It's just, what would you call that? What's Na in NaCl? Sodium, right. So any binary ionic compound that Na or sodium makes, we don't change the name. It's just sodium stays sodium. That's all that's saying. There's nothing tricky. There's no extra prefixes. It's not disodium or trisodium or whatever. It's just sodium. It's always just sodium. So then the monoatomic anion, that is the single atom anion, you cut the end of the word off and you put "ide." So chlorine, which is Cl, becomes chloride, which is Cl minus the anion. And that's how we determine an anion from a neutral compound. With the cations, we don't change the name. So a sodium ion gets the same name as a sodium atom. With the negative ones, we do. So chlorine becomes chloride. What do you think N3 minus would be called? Nitride, right? You've got nitrogen, so you cut out the ogen and you make ide. So N3 minus becomes nitride. And then the book gives us these little colored boxes to help us remember the different types of things. Once you put something in this category, it's always going to be named by just saying the name of the cation and then the name of the anion with ide. So looking at some of these examples, let's see if we can name them. CaO, what are you going to call that? Calcium oxide, right? Calcium from the Ca and oxide from oxygen from the O minus. What about SrF2? Strontium fluoride. And K2Se? Potassium. You want to check your periodic table for this one. Selenide, right. Se is selenium. So K2Se is going to be potassium selenide. See how that works? Pretty simple. The tricky part about this is when we get into the other ones, people always want to name these simpler ones with all the more complicated rules that we're going to get into next. The trickiest part of this category is remembering that when it's in this category, that it's simple. You just put the name in there. You don't put any extra numbers. You don't put any extra prefixes or anything like that. It's just the cation and then the anion with ide. Okay. So let's look at a different type of ionic compounds, of binary ionic compounds. This is where it starts to get a little bit tricky. Some cations, specifically the ones we've just talked about, only form one charge. There's only one type of ion that these can form. Examples, everything in column 1A only forms what type of ion? We talked about this last week. What charge does it have? +1. They're all going to be +1. Column 2, what are they going to be? +2, right. What about column 6B? Do we know? Which is also known as 6. Yeah, we don't know. Because, in fact, all those middle ions can have a variety of different charges. So all those, that kind of chunk in the middle, which are known as the transition elements or the transition metals, can have various different charges. So when we name a compound, we need to specify that, because we could be talking about two totally different compounds. So example, iron can be either 2+ or 3+. Two different ions can be formed by iron. And so we need to have a different way of naming so that we can differentiate these two compounds, because they're actually totally different compounds. They have different ways of reacting. They look different. They need to have different names so that we know that which one's which. So we can't simply say iron chloride, because iron chloride is not specific enough. So the way that we do this, and some people would say this is a little bit confusing, but I think it ends up working out okay, is we take the name of the cation, so iron, and the name of the anion, chloride, just like before. But now we put in the middle, in between the two, the charge of the cation in Roman numerals. The Roman numeral indicates the positive charge on the metal. So that means that FeCl3, what's the charge on the metal? It's 3+, because we need 3 chlorides to balance it out. So we would call this one iron 3 chloride. And then Fe2, oh, this is talking about the other system. That's fine. We'll look at both of them. I don't want you to get confused, so I want to emphasize this type of naming. This is what we're going to ask for when I say, what is the correct name of this compound? We're always going to use that Roman numeral notation. Now, for some common ions, they have another name where the one with the higher charge gets ic and the one with the lower charge gets us. So another name for this would be ferric chloride, and then another name for this one would be ferrous chloride. That's a little bit of a tricky and confusing way to do it because some atoms have lots more than just two different charges. And so then what do? Then they have all kinds of different names. Or sometimes ferric, or sometimes the ic means +2 and the us means +1. So it's much less specific of a name. So I don't want to worry too much about those names. I want to focus on the standard naming conventions which use that Roman numeral. Okay. Let's see if we can name these using that convention then. What would you call CuCl? Copper chloride, but we have to be a little bit more specific. Because copper can have multiple, copper's in the middle, it can have multiple different charges. So what's a better way to name that? Copper 1 chloride, right. Copper 1 chloride. What about CuCl2? Copper 2 chloride. What about HgCl? Mercury 1 chloride, and this would be mercury 2 chloride. Oops, not quite into there yet. Okay, let's look at a couple different ones because sometimes this can get a little bit confusing, and so I want to show you why or where that might become confusing. Cu2O. So we look at the periodic table and we see that Cu is in the middle, and that means we're going to have to specify a number. We can put the other words down. We know the other words. We know it's going to be copper oxide, not oxider. Copper oxide. What we don't know is what's going to be in that parentheses. So how do we figure that out? Yeah, and that's really the key here. The Roman numeral indicates the positive charge on the metal, not the number of atoms in the formula. So in this case, what's the charge on copper? It's actually +1. How do we know that it's +1? Yeah, because an oxide ion is -2. How do we know an oxide ion is -2? It's always -2, so it's a good one to just know. But you can also figure it out in the periodic table. Things in that second row from the right are likely going to make a -2 anion, just like things in the first from the right are going to make a -1, and things from the third from the right are going to make a -3. So we can kind of guess it that way. And then we know that oxygen is -2 or oxide is -2. That means that if there's 2 coppers and 1 oxygen, each copper must be +1 to balance out that charge, right? So this becomes copper 1 oxide. Okay, that is sometimes misleading to people because there are 2 coppers in the formula. So they see Cu2O and think, oh, well, it's copper 2 oxide. But it's actually not. What would the formula for copper 2 oxide be? CuO. It would just be CuO, right? CuO would be copper 2 oxide. Let's write that. So CuO is copper 2 oxide because now we have +2, -2 in the neutral compound. So that's the only real tricky part about this type of naming is figuring out what that charge is and remembering that that number is the charge on the metal, not the number of something in a formula. So you have to look at the anion, figure out the charge on the metal, and then go from there to figure out the name. Okay, The other question about this type is determining whether something is a type 1, the ones we talked about before, or a type 2. So remind me again, what's the difference between these types? Whether or not you need the parentheses, how do you know? How do you know if you need those parentheses or not? Yeah.
When it's like one of those in the middle, right?
Yeah.
I'm not sure.
So anytime you don't know what the charge is, you have to use that. You have to use that convention. You have to use the parentheses. And if it is only one possible charge, then you don't use the parentheses. And it's actually wrong to use the parentheses if it's a known charge. So let's look at those. There's a list in your book. I was going to say let's put it on a periodic table, but I guess we can just put the list in here. Losing all my supplies. So this would be on page 97. You see this table over here? Let's see if I can copy it over. Let's make ourselves an extra page here and look at this chart. Okay, so this table a little bit is atoms metals whose charge is invariant from one compound to another, which is just a fancy way of saying it only makes one ion. And that's a big list to remember, so let's group them, right? The group number is the important part. So everything in that first column, in that first group, everything in that second group, and then here are kind of the weird ones. So you got 4 weird ones. Just remember 2 big lines and then 4 weird ones. And actually, so the weird ones are aluminum over in 3A, zinc over in 2B, so the very edge of the transition metals is always 2+. Scandium, the very beginning of the transition metals, in 3. And silver, which is kind of randomly right in the middle at 47, at number 47. So those are kind of the weird ones that you just have to remember. Those charges don't change, so we don't use the parentheses here. So when we see those metals, we do not put the charge in parentheses. We do not put that charge in the middle. We just name it as type 1. Anything else, all that other middle stuff, we have to put that charge. Okay. You can do that? Maybe? All right. Let's look at the next type of ions. Whoops, I didn't mean to do that. There we go. So there's kind of another type. It still fits in these binary ionic compounds, but the ions can be a little bit trickier. And that is the polyatomic ion. So probably in a previous class you had to memorize a bunch of polyatomic ions, right? Remember doing that? Well, good. You get to use them again here. These are ions that are made up of multiple other atoms. And as it says up there, these must be memorized. There's no magical formula of figuring out how to do this, how to figure out the ions. You simply have to know them. And so there's a table on page 99 of the ones that you should know. And probably some of these you already know. Hopefully some of these you already know. Just the table right here. We have it. Oops. Here's that table. Okay. Do you know some of these? Can those look familiar? I don't know if you can you read that from where you are? Maybe. So those you just need to know the name of, and you need to be able to recognize them in a compound so that you can name it accordingly. So if we come up with something like NH4OH, how are we going to figure out how to name that? Is it nitrogen, hydrogen, oxide, hydride? It's not, although I've gotten that on an exam or something like it many times. You have to recognize that those are ions made up of nonmetals. So NH4 is an ion, and OH is an ion. And there's no way to figure out what that thing is called or what the charge is. There's no like technique to that. You just have to know it from the table. So looking at the table, what's NH4? Ammonium, and it's a charge of +1. And what's OH? Hydroxide, and that's a charge of -1. Right. So we've got ammonium hydroxide. We put those names together, and we've got the name. So these are actually named just like the type 1s. We don't put any charges in there. We don't have any parentheses. But we need to know the names of the ions, or we have no chance of actually getting that name. All right. So let's go down the list. NH4Cl, how would you name that one? Ammonium chloride, right? Ca2CO3. Calcium carbonate. Right, that one's right up here, carbonate. CO3, 2-. And actually, that's the wrong formula for calcium carbonate. Have you noticed that? Calcium is +2, carbonate is -2, so that should just be CaCO3. NH4NO3. Ammonium nitrate, right. KNO3. Potassium nitrate, and Na2SO4, sodium sulfate. So note that we don't put any prefixes. We don't say disodium sulfate or something like that. We just put the names together just like in that first category. You take the name of the cation and the name of the anion. And these you don't even have to change the name of the anion because they're already, that's just their name. All right, so what is this? 1, 2, 11. So it's about 23. So once you know these 23, you should be in good shape. I don't think we'll see too many more than that. There are a couple shortcuts. They're not great. But there is, let's look at these chloride anions for a minute. You'll notice a pattern here, that the more oxygen they have, they keep the same charge, but add oxygen and get different names because of it. So perchlorate has the most oxygen, it's ClO4. Then chlorate, ClO3, then chlorite with an I, ClO2, and then hypochlorite, ClO. So if you want to remember that progression of names, that can sort of help you because it also comes up in, for instance, sulfite and sulfate. Sulfate has more oxygen, sulfite has one less. Same with nitrate and nitrite. Nitrate is going to have the most oxygen, nitrite has less. The tricky part about that is it's not always the same number. So like chlorate is ClO3, but sulfate is SO4. So it's not always the same number of oxygens, but the trend to go from 8 to 8 by losing an oxygen, that stays the same. I don't know if that's helpful or not. But these are some names that you should know. And the best way to do this, of course, there's lots of ways to memorize things. There's flashcards, there's apps, there's stuff on the internet to help you memorize things, and those are all great. But also just working through problems, working through names. Once you encounter nitrate 20 times, you're probably going to remember what it is just by working out those problems that many times. Okay. So then let's look at our final class, and then we can start just doing some examples and looking at some different names. So our final class of compounds is going to be the binary covalent compounds. The important thing about the binary covalent compounds, generally these are non-metals, and they do not contain ions. So these are not ionic compounds. And we'll get into kind of some of the more specific aspects of what that means later in the semester when we get into atomic orbitals and bonds and things like that. But for now, we know a little bit of that ionic means transfer of electrons or charged particles, and covalent means that electrons are shared. For you, from like a strategy of how do you actually figure out these names standpoint, the best thing to remember is that these type 3 or binary covalent compounds, these tend to be non-metals. So we're talking about non-metals with other non-metals. And for whatever reason, these are the names that everybody likes the most. Because when I grade these and they're wrong, a lot of times it's because somebody tried to name some other stuff using these rules. So I don't know why everybody loves these rules so much, but this only applies to binary covalent compounds. And you're going to use the full element name for the first element. The second one is named as if it's an anion, even though it's not ionic. And then you use these different prefixes to note the number of atoms present. So you got a prefix in a first element, then a prefix in a second one. And that's how we get things like CO, carbon monoxide. You've probably seen that one before. You get your carbon, and then there's one oxygen, so there's carbon monoxide. Mono is a prefix for just one. What would CO2 be then? Carbon dioxide. So di is the prefix for 2. And do I have a list of prefixes here? I don't, so let's write them down. We've got mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, and hexa for 6. And we won't get much higher than that in the compounds that we see. We won't get higher than that. We'll generally knock off that A or O when the thing starts with a vowel. So we don't say monooxide, we just say monoxide. We don't say tetraoxide, we say tetroxide, just to make it kind of sound better. And then the other trick from this is we don't put mono at the beginning when there's only one on the first element. So CO is carbon monoxide, SiO2 is silicon dioxide, and it's not monosilicon dioxide or monocarbon monoxide. And that's just to make it simpler, I guess. So let's fill these in. We got a few different names here. Some of them are given. Let's see if we can fill in the ones that are not given. So N2O, we call that nitrous oxide. That's laughing gas. But what is its actual systematic name? What do you think? How do you think we should name it using that rule? Yeah, what? Close. Yeah, dinitrogen monoxide. So that tells us there are 2 nitrogens and 1 oxygen. Dinitrogen monoxide. What about N2O3? Yeah. Dinitrogen trioxide. And N2O5? You might want to give that one a try. These are all real compounds, by the way. They all exist. Yeah, that would be dinitrogen pentoxide. Okay, so here's some practice. Let's do a couple of these and then we'll take a little break. We'll do these first 4. So now I'm not telling you what category these fall into. So you have to figure it out. How are we going to do that? What's a good way to think about this in your brain of where these things are going to, what category they're going to end up in? Any idea? How might you think about this? Just in general. Yeah.
Look to see if there's a metal there.
Yeah, that's what I would say first, is look if there's a metal. Because if there is a metal, that tells you it's what, generally? It generally is going to be ionic. If there's no metal, then it's going to be covalent. So in this first example, P4O10, what would that be? Covalent or ionic? Covalent, because there's no metal there. Both of those atoms are on the right side of that line that we talked about. So we know there's not going to be a metal. So that means that we name it using those last rules that we just talked about. So that, what would that be here? We didn't get to the 10, but 10 is deca if you're... Yeah. Or deca oxide. Now, normally, actually, this is named as P2O5, which is diphosphorus pentoxide. But that's how you would do something like this. You don't have to know that up to 10. What about NB2O5? Same choice. Is this going to be ionic or covalent? And how do you know? You said ionic? Why ionic?
It's a metal.
Yeah, NB, anybody know the name of that? Niobium. Yeah, it's niobium. That's number 41. So right in the middle of all the transition elements. That's definitely a metal. And oxygen is a nonmetal. So you got metal, nonmetal. That tells us it's covalent. Okay. Or I'm sorry, that tells us it's ionic. Ionic. Let's write that down. Once we know it's ionic, what's the next question that we have to ask to get the correct name? Yeah, the charge. Is it a fixed charge? Do we know the charge of niobium always? Is it always the same? Or is it variable? Variable. So variable charge. Well, first we decided it was ionic, and then we decided that it had variable charge. So what kind of a naming is that going to be then? And what category? What? Yeah, what we call type 2, where we have the metal name, parentheses, and then the non-metal name. So in this case, we know a couple of those. We know that that's going to be niobium something, and then this is going to be oxide. So our last part of the name is just figuring out what goes in those parentheses. So how do you figure that out? Yeah, we have to balance it out. So what's the charge of oxygen oxide always? -2. So if there's 5 of them, what's the total charge, negative charge there? -10. So then what does each of the 2 niobiums have to be to balance out that -10? 5. So that's going to be niobium 5 oxide. Now, we should note that these high charges are not actually charges, so to speak. That means that a niobium 5 is not actually a true 5+ ion or +5 ion. It's actually what we call an oxidation state, which means that some electrons are removed, but only because it can then bond to oxygen in a slightly more complicated way. So this compound, NB2O5, is not actually a truly ionic compound because of the intricacies of how that bonding works. And if you want to talk about that sometime, we can talk about that sometime. But we still name it in that way, so we can pretend it's regularly. We can pretend it's fully ionic for our purposes of naming. Okay. How about C, Li2O2? Lithium 2 oxide. What's the problem with that? Yeah, lithium can only be +1. It's in the first column. So how do we deal with that? What is that? Is there an error here, or is something weird going on?
It doesn't balance out.
It doesn't balance out. Why doesn't it balance out?
Lithium +1, oxygen is -2.
Yeah, lithium is +1, oxygen is -2. So what's going on here?
Oxygen occasionally has different ions.
Oxygen in one case can have different charges. And that's because O2 is actually a polyatomic ion. Let's go up here. So O2 can be a polyatomic ion known as peroxide. And in that case, yes, each oxygen has an oxidation state of -1. But the ion overall is a 2- ion. So now that works. So then knowing that, how do we name that Li2O2? Yeah, this just becomes lithium peroxide, now that we know that that's a polyatomic ion. All right. And the last one before we take a break, TiNO3,4. First of all, is it going to be ionic or covalent? It's ionic because of that titanium. That's Ti, titanium. And does titanium have a fixed charge or variable? Variable, being in the middle. So that's going to be another one like we just saw, where we've got this, parentheses, and then this. So we know that this is titanium. What's the other ion? Nitrate. And then what should the charge be on titanium? 4, how'd you know? Right, nitrate ion has a -1 charge, and there's 4 of them. So that means we need a 4 plus titanium to balance that out. All right, so titanium 4 nitrate. We're good? All right, let's take a break. It'll take about 15 minutes, and then we'll come back and go the other way where we find the formulas from the names and talk about some acids and a couple other things.